All right, so what we're going to talk about today is finishing off the discussion about concurrency and streams. Last time we had talked about what a stream was in general, and I showed you a simple example of a sequential stream. And what today we're going to do is talk about parallel streams, which is essentially applying concurrency mechanisms to streams to more or less transparently speed them up most of the time. So in the first part of this lesson, we're going to talk about how Java 8 leverages the functional programming features that it provides in order to support this notion of parallel streams. So we talked before about aggregate operations. We talked about things like map and filter and collect and so on. And these aggregate operations work for both sequential and parallel streams. So the good news is once you've got yourself a sequential stream, then it's often, though not always, pretty easy to scale it up to work in a parallel stream with minuscule changes. The secret sauce here is you have to make sure that the code you write doesn't have side effects that yield race conditions. So as long as you're able to partition your data in a way where different parts of the stream can run independently with no dependencies, in other words, embarrassingly parallel, then the mechanisms we're going to talk about work really well. If you don't have that, then you have to apply locks, which is not a hard thing to do if you know how to do synchronization, but it's not quite as drop-dead easy as just taking a sequential stream and changing one thing, which is the ideal goal. As I mentioned, the difference between a sequential and a parallel stream is often minuscule. And in particular, if you recall our discussion about the search stream gang, we had a stream that looked like this. We got an input of the input to search. We turned it into a stream. We mapped each element in the stream, each input string, to this process input method, which returned a list of search results. And we collected them all together into a list of search results. And that was the sequential version. Here is the parallel version. The only thing we do is we go from saying stream to saying parallel stream. And again, assuming that you've set things up properly, boom, all of a sudden things are going to run a lot faster. And I'll show you specifically how much faster in a second. After we talk about parallel streams, I'll show you a run of the program, and you'll see the difference it makes. OK, so internally, Java 8 Streams framework uses a Forkjoin pool executor. So we've talked about the executors before. We talked about the fixed executor, fixed size thread pool. We talked about the cached thread pool executor. Now we're going to talk about this thing called the Forkjoin pool executor. And internally, this uses something that is called a MapReduce-like model, where it splits algorithms up into pieces so they can be processed concurrently by different threads. So imagine you have one big task. Then what you do when you use the Forkjoin pool executor is internally the Forkjoin pool takes the big task and it breaks it up into a bunch of subtasks. And I'll walk through this more in a second to show you how each piece works. These, of course, work for embarrassingly parallel programs quite nicely. And they're also an example of this so-called MapReduce paradigm. You're most probably accustomed to hearing about MapReduce in the context of web services and web searching. That's what Google uses when it does searches. And this is sort of a multi-core MapReduce as opposed to a multi-machine MapReduce, which is what Google would do. The actual splitting of the tasks up into smaller pieces is done by something called a splitterator, which is a fancy kind of iterator that works for concurrent streams. And what it does is it basically divides the work up into smaller pieces that the Forkjoin pool then executes. So let's take a look at see how this works. So you have a task with a bunch of work to do. And for example, you might have a list of input to search, list of strings to search. And what the Forkjoin pool does is it takes that original list. Let's say you have 20 lists of strings, or sorry, 20 strings. And it goes ahead and it breaks it up into chunks. It forks into 2 subtasks. And then those things will get forked into smaller subtasks. So by the time you're all said and done, you might actually end up with 4 subtasks, each of which have, say, 5 input strings to search. And that's all done magically behind the scenes. You don't see, you don't know what's happening. That's just what it does for you. And then what happens is all these subtasks are stuck onto work queues. We'll take a look at how those work in a second. and then they're processed by a pool of threads, where the size of the pool is typically a function of the number of cores. And so as the tasks complete, they're joined together. So these two things finish, and they join together to get this result, likewise over here. And then by the time you're done, all the subtasks, after they're processed, all their results are then joined back together, and finally there's one result for the whole thing. So that's kind of how a Forkjoin pool executor works. Now, the thing that makes this kind of interesting is they use a mechanism to implement this called work stealing. And here's the idea. So to take a step back, the big picture view here is that on modern multi-core processors, it's a bad idea for the cores to ever have to go to sleep, because it takes a long time to put a core to sleep, a relatively long time. For a core to go to sleep, we're talking about tens of microseconds, but that's a long time. And so rather than have things go to sleep, what you want to have them do is continually be active. And the way they stay continually active is if one thread runs out of work in its queue, it will then go and steal work from another queue in order to keep going. Now, the way that this works under the hood is it uses something called work stealing queues, which are actually decks. Does anybody remember what a deck is? A deck is a double-ended queue. So a deck allows you to be able to insert and remove from the head, and to be able to insert and remove from the tail. So you can do both those operations in parallel. And of course, the way it works under the hood is they use separate locking structures, so you can add and remove things at the end or the beginning of the deck without having to worry about contention. So let's imagine a scenario where we've got several decks and we've got several threads, and for whatever reason, the one in the middle gets done earlier than the other ones because their workload might just be faster for whatever reason. So it no longer has any work on its deck. Well, rather than go to sleep waiting for more work to show up, which would be inefficient, instead what it does is it goes and it steals work from the end of another deck. So you can see here it grabs a subtask to process off the end of the deck, and then it goes ahead and processes that. And this is what's called a circular work stealing deck. And you can go here and read more about work stealing decks, and you'll find out how this stuff works under the hood. So pretty cool idea, not perfect. I'll talk later if we have time about some deficiencies with this approach, but it does have some benefits, and especially for things where the goal is to keep the processors humming along, doing work as much as possible. That's really the benefit of a work stealing approach. You can also take a look here. There's a nice interview with Doug Lee, who's the guy who wrote all this stuff in Java, and he talks about the Forkjoin abstraction and how it works. It's a really interesting interview with him. By default, the size of the Forkjoin pool that's used by all the Java 8 parallel streams in a process defaults to the number of cores available to the Java virtual machine. You can change this number if you don't like what you get out of the box. By doing something like this, you can change the number of threads that are in this common Forkjoin pool. But be aware that doing this will affect all the parallel streams in a process. So all the streams in a process that are parallel streams all share the same pool, which I think is actually kind of weird, but that's the way it works. So that's one of the limitations. OK, so that's the end of part one of the lesson. So now that I've given you an overview of what a parallel stream is at a high level, we'll take a look at an example. This example will improve what we had talked about earlier to give a parallel version of the search stream gang that we had talked about in its sequential form in the earlier lesson. So there's two different parallel streams that are used in this particular implementation, and we'll take a look at how they get applied. There's actually a program that I'll run for you in a second that has a bunch of different ways to implement concurrency for doing this processing, and here are the outputs from this. And as we see when we take a look at this later, the results from the program are printed out in ascending order from fastest to slowest. And what you'll see here is that the sequential versions typically take a long time to run, whereas the parallel versions run much faster. In fact, you can see here that this is almost a linear speed up in the number of cores at our disposal. This particular example ran on a quad-core machine, which is the machine I'm running here right now. And you can see that the sequential versions took almost 4,000 microseconds to, milliseconds to execute. And in contrast, the parallel version that we're about to look at took less than 1,000 milliseconds to run. So you can see it's almost linear speed up, which is pretty cool. That's, of course, reflective of the fact this is an embarrassingly parallel program, right? All right, so we're going to have process stream, which will use a parallel stream to concurrently search a list of strings. And then we'll have process input, which will use a parallel stream to concurrently search each input string for all occurrences of words defined. And under the hood, of course, this all uses the Forkjoin pool stuff we were talking about before. So it turns out that making the sequential version a parallel version is absurdly easy in this case because the way the program is designed. All we do, literally, is change stream to parallel stream. Everything else stays exactly the same. Uses a splitterator under the hood to take the list of strings, break them up into smaller chunks, and then run them in different threads to process those various chunks. Here's the process input method. Once again, the results are absolutely trivial. We just replace stream with parallel stream, and then we're able to go ahead and process all these things concurrently. Everything else is pretty much the same, uses a splitterator under the hood as well. Now here's the deal. For this particular example, because it's fundamentally an embarrassingly parallel approach, going from a stream to a parallel stream was easy, and it got essentially linear speed up, as we'll see when we look a little bit more closely at the code. That doesn't always mean that this is the right thing to do. Now, for many cases, if the choice is between purely sequential versus concurrent, then going from stream to parallel stream is often the fastest way to get concurrent processing without having to do sort of any more head scratching and parallel design. However, it turns out that there are even faster ways often to be able to speed up your program. And we probably won't have time to talk about them in this class, although you can take a look on the web. I have some other videos that talk about that. And the more efficient approach is to use something called completable futures, which is an asynchronous concurrency model for being able to do things even faster. And that works especially when you have I/O-bound jobs where you really get a benefit from asynchrony. So your mileage may vary. There's no substitute for systematic benchmarking. You always should benchmark your code. By the way, one of the things to remember with anything involved with concurrency is the fact that your results will depend on many factors. They'll depend on the hardware platform you've got, the number of cores. They'll depend on how much memory you've got. They'll depend on the workload that you have, the kind of input, and how you program your solution. So it's often very hard to know exactly which is the right version in the abstract. And even if you benchmark your solution, it may take a while because you may not always have all the right data to indicate exactly how things work. But benchmarking is very important. The other thing to remember, too, is that when you have concurrent programs that run on multi-core processors, there invariably will be bugs in your implementation, and so you have to be prepared for that. And it's often hard to find them and fix them because they tend to arrive in a non-deterministic way. What we have now open is the source code for the search stream program. And if we poke around here, we'll find we have the driver program, and we have a set of various kinds of search streams, parallel and sequential and so on. And there's also some other things in here that we won't sadly have enough time to talk about. One of the other things that's become very popular in Android and Java programming these days is something called RX Java or RX Android, which is a so-called reactive variant of programming. And it's really interesting, and it makes concurrency very easy to do often. Very different way of looking at the world. It's much more functional in its nature. And an event-driven, it's sort of a reactive event-driven programming model, which is functional. We won't have time to talk about that, but that's a really cool topic. And if you want to see how the code works, you can take a look at the examples that also search for strings in input strings, search for words in input strings. Let's go ahead and run this program. So I guess a little hard to see this. So what this is doing is it's going through and it's running each of the different ways of doing searching for words. So we have the sequential version, we have the parallel stream version. Those are the ones we've looked at so far. And then we have variants of all this stuff, things using completable futures and so on, things using RxJava, and so on and so forth. And I'm not going to go through all that in detail. What I want to show you is the results, which, again, may be a little hard to see, but I'll read them to you. So, oh, and then also, we have some hard-coded versions that compare and contrast with the framework implementation that I've developed. So we had two different input sets here based on different kinds of input. The first one had larger amounts of input, so it takes longer to run. And this basically produces the outputs in sorted order. And so again, it may be hard to see, but over here you can see that the sequential stream version, which is the one we looked at in the previous lesson, took about 4,666 milliseconds to search all the different input strings. And in contrast, the parallel streams version took 1,335 milliseconds. That's the one we just looked at. So just changing stream to parallel stream made everything run a lot faster without having to do anything else. So that's pretty cool. Then there's a couple of other implementations that use completable futures and RxJava. And again, it may be hard to see there, but these are even faster. So they're about 1,081 milliseconds. So distinctly faster than the sequential stream for sure, and also faster than all the other parallel stream implementations. So the point of all that just is that there's improvements you can get from concurrency and parallelism on a multi-core machine, and you may need to do a couple of different approaches to find the one that works best for your particular implementation. And again, we won't really have enough time, sadly, to go through all that in detail, but it's pretty cool, and you can take a look at the code here if you have more questions. Okay, now that we've taken a look at a very simple example of parallel streams, which was just a concurrent version of our sequential search gang program from earlier, we're now going to take a look at a more advanced example. And this example will be based on something called the image stream gang. And an image stream gang does basically downloading and processing of images that it gets from the network or from a local file cache if we just want to test the concurrency models. And I'll talk about what the program does, and we'll see how we can use streams. This will also introduce us to much more interesting mechanisms available in parallel streams. So this example works as follows. First of all, you'll see when we look at the implementation in more detail, it combines both object-oriented and functional programming features into a common solution, which is really cool. And what it does is it will get a list of URLs to download from the user or from a file if you pre-configure it for testing, and it'll ignore any images that are already downloaded and cached. It will then download from the web server or web servers any non-cached images, so it goes out and grabs those things using network calls. It then applies a list of filters to each image, and those filters, as we'll see, can do various kinds of image processing on the images that are downloaded. And then it stores the resulting filtered images to the file system on the local device. So it's downloaded them from the network, puts them into the file system, and then ultimately will display those things to the user. That's actually done with a separate activity, but everything else is just used to download the images, filter them, put them into the file system. So it'd be interesting to see, how would you write code like this if someone just gave you that as an open-ended assignment? Well, what we're going to do, of course, is we're going to apply streams, and what you're going to see here in a second is that the parallel stream approach is essentially sort of a one-to-one mapping of each of these requirements, or each of these descriptions of what we're doing onto a element, an aggregate operation in the pipeline of streams that get processed. And the cool thing about this is by doing it this way, we kind of close the gap between the design intent, which is the stuff here on the left, and the implementation, which is the stuff here on the right. So the cool thing about functional programming in general is if you do it right and you understand how the mechanisms work, when you read your program, it looks an awful lot like the specifications of your program, not the implementation. The implementation and the specification are closer together in terms of how they're described. So we'll see here that we're going to write an aggregate operation to ignore cached images, and it'll look like this, and I'll talk more about this in a second. What it's going to do, it's going to filter out anything in the stream that is already cached, It's then going to go ahead and download the non-cached images. And again, that'll be done with a filter called, or it's not a filter, by a map aggregate operation. It'll apply a list of filters to each image, and it'll use this funky aggregate operation called a flat map, which is pretty cool. And then it'll finally store the filtered images into the file system. That's also done as part of this step. And then it'll collect everything up into a list of completable futures to all these things, and that will eventually trigger stream processing at all the end. So the cool part about this is the code that you write looks almost exactly like the spec, and so the streams framework is going to orchestrate all the various steps involved, and making this thing run concurrently is an absolute snap. And so we'll talk about that as well. OK, so let's talk about how we might do this. So here basically is the process stream method that we're going to have that's going to do all these different kind of things. You can take a look at that here at this link. So what we're going to do first is, in this particular case, we have a list of URLs. So remember before, when we talked about the search stream gang, we had a list of input strings. Now we're going to have a list of URLs that we want to download. And that could be big or small. Let's say that we've got dozens of things we want to download. So we get that. That comes back as a list of URLs. And then we go ahead and we say, I want to run all of these things in parallel. So we make that a parallel stream. So that converts the list of URLs into a parallel stream. Now under the hood, what goes on is the split iterator mechanism that's part of Java takes that list of URLs, and it knows how big it is, and it goes ahead and it splits it up into smaller parts. And then those smaller parts are handed off to different threads in the thread pool. And they will eventually go ahead and do all the processing steps we're about to talk about. So we now go ahead and take that stream that we broke up, and we start applying aggregate operations. The first one is to filter things. And what that basically does is that's going to go, and for every item, every URL on the stream, it's going to go ahead and call this function. And that function is going to go to check to see whether that element, that URL, has already been downloaded and has been cached. So if it has already been cached, we want to ignore it. So we're going to filter anything that's not cached. What that means is if it hasn't been cached, we're going to let it through. If it has been cached, we're going to ignore it. So filter is going to return an output stream that's going to consist of the URLs from the input stream that are not in the cache. And it takes a little while to get your head around the not of the cache. But once you understand that, it's basically just saying, get rid of everything that's been cached. And that's pretty straightforward, right? You can just look at that description. You can look at that line in the stream. And once you know what URL cache does, you're like, oh, yeah, it's going to filter stuff that's, it's going to let stuff through that's not cached. So you're just saying what you want done. You're not describing the mechanism for doing it. That's hidden in the function like URL cached and not, and filter. OK. So then what happens is it takes the list of non-cached URLs, which is likely to be smaller than the original list, and then it's going to go ahead and call map. So for each of those URLs, it's now going to call this method called download image. And what download image does is download image goes out, and it actually downloads the image. Now, the way this works under the hood, we wouldn't want to have download image called in the main thread of control because it would block everything, and that would cause the dreaded application not responding error. So instead, what's going to happen here is that the download image method is going to be run in a thread in the thread pool. So it won't block the main user interface thread. I do have to mention one little aside here. It's kind of funny. This is Java 8. And when you run Java 8 in Android, the Java 8 implementation doesn't know anything about Android's weird constraints on the UI thread being special, right? So remember, in Android, if you're in the UI thread, you can't do long-running blocking operations. So if you have a parallel stream that's called from the UI thread in Android, it will include the UI thread as part of the pool of threads that it uses to run the tasks. So some of the stuff will run in background threads in the pool, but other stuff will run in the UI thread. So you'll get abysmal performance and probably get application not responding errors. So when you use parallel streams in Android, you typically have to create a separate thread, a background thread, to run the parallel stream. And that way it doesn't include the UI thread in the threads that are included in the pool of threads. Just a little quirk that is important to understand if you're trying to use this in Android. So the map operation will take each URL that hasn't been cached yet. It'll call the download image method. And the download image method will basically go out and open up a connection to the web server at the URL, download the content, and store it into a local file. And that'll all run in the background, so it won't block the UI thread. So when this thing is done, we will end up with a list of basically so-called image objects, where an image object corresponds to what has been downloaded. And the number of output stream elements from map always matches the number of input stream elements. So whatever we didn't throw away in this filter step, we've now downloaded those images. Now, of course, if the download had failed, you'll have to return an image that indicates it had failed. So you'll always get back an image, but you'll have to indicate somehow in its state that it doesn't actually have a valid downloaded chunk or file that goes along with it. All right, now the next step is kind of interesting, and this is going to introduce us to yet another aggregate operation called a flat map. And this is a little different from the ones we had before. So here's the deal. So what we've got now is we've got a list of images that have been downloaded, and they're image objects. So that we actually don't have files created for them yet. We just have images that have been storing their data as part of the image object. And what we're going to do now is we're going to have a list of filters to apply to each image. So we might have a grayscale filter, or a charcoal filter, or an embossing filter, or a red eye removal filter, or a null filter, right? You know, whatever the filters are that you want to apply to these images to process them. We're going to have a list of those things. And so the result of applying the apply filters method to the list of images that have been downloaded is going to be a bunch of files, each of which corresponds to whatever filter was applied to the image. So for the grayscale filter, we're going to make a file that's the result of applying the grayscale filter to the image, and it'll go into a separate file. For the embossing filter, we're going to go ahead and apply that to the image and put that in a separate file. So the key thing to note here is that apply filters is going to return, assuming you have more than one filter, you're going to have many output items for each input item. So that's different from map, right? Remember, map always gave you back the same number of elements that you gave to it. It just maybe transformed them in some way, say going from a URL to an image object, right? But when we do flat map, we're now going to end up with more stuff. And so apply filters is going to take in the image object, and then it's going to apply the filter, and it's going to create the output object. And so what flat map does is it basically takes the input and then creates a bunch of output streams, which it then goes ahead and turns into a single aggregate output stream. So flat map returns a single stream that's flattened all the other parts. So it looks like a single stream, or it is a single stream, but it actually may contain multiple output elements from the input that came to it. So the key point of flat map is you typically want to use it when the number of output stream elements differs from the number of input stream elements, and in a way that's more unconstrained than simple filter, which it always will give you the same or less. This can give you the same or more. Yeah?
What it does is like concatenating arrays.
A good way, it's concatenating streams. Yeah, a good way to think about what apply filters is doing is every time you, or flat map, whenever flat map calls the method reference, or lambda, that's passed to it, that lambda or method reference returns a stream, and flat map concatenates each of those streams to turn it into one stream. But it's actually concatenating the streams, but it's turning them into the elements of the stream. It's flattening out the elements. So you end up with one stream with all the elements that came back from the function that's applied. Austin, do you have a question? Okay. So that's what flat map does. Flat map is really powerful and very interesting. So finally, just to make this concrete, let's say that we had 6 images, and we went ahead and ran this, and let's say, for sake of argument, that one was already cached, so we end up with 5 images. We download those 5 new images, and then we go, let's say we have 2 filters. We have an embossing filter and a null filter, or an embossing filter and a grayscale filter, or whatever. After we call apply filters and flat map, we'll now have a stream with 10 files that store the filtered images. Because we had 5 things we downloaded. We applied 2 filters to each one. Now we have 10 that just make it concrete. And what collect does is collect then goes ahead and puts them all together into a list of images that have been filtered and stored in files. And then at this point, we can print a result or display the result or whatever we want to do. So collect is essentially what's called a reduction operation that combines all these elements into a single result. OK, so that's basically an overview of a more interesting example. Again, we won't have time to look at all this code in great detail, but I'll show you some of it here in a second. All right, so let's go ahead and OK, so this is the source code for the image stream gang example we just looked at. This will just give you an overview kind of the high-level structure of the test program. You can see we have different tests to run. We have a sequential version. We have a parallel version. We have versions that uses completable futures. I won't go through those right now. We have a couple of different filters. We have a grayscale filter and a null filter, which doesn't filter anything, just there as a placeholder. And then the actual program is going to iterate through all the tests, and it'll go ahead and make the appropriate kind of stream gang, image stream gang to do the testing, and then it runs the stream gang and stores the results. So let's go over and take a look at the sequential version of this stuff. This is the version that does what we just talked about a minute ago, except it does it sequentially. So you can see it's got the same steps. We filter out everything that's not cached. We download stuff. We apply the filters, and we're done. So let's take a look at some of the helper methods here that actually do this work. So here is the one that checks to see whether an image is already cached. What we do here is we go through the list of all the filters. And if you recall, here was the list of filters, null filter and grayscale filter and so on. And for each filter in the list, we go and check to see if that filter and file URL has already been downloaded into the cache. And if it's already there, then count returns greater than 1. So that means it's been cached. And so we take that result, and then we negate it by the not operation. So that inverts the test. So we only let through the ones that are not cached. So that's just a simple example of a little helper function, and we pass the method reference to that helper function here, and then we negate it via a predicate. Let's take a look next at the download image. So to do the download image, I think we have to go up a level. So here, I hope, is download image. So this is a really simple method. Download image is simply going to make a new image object, which is going to download the contents of whatever image happens to reside at the URL we passed in as a parameter. So all it does is just makes an object that stores the bytes that were downloaded from that URL. So really simple. So that's what download image does. So if we come up here, you can see that once we filter stuff out, we then download each of the images. And then the next method, which we'll look at, which is called in flat map, is going to actually do the filter processing on each one. And you can see here we have a little bit more interesting stream this time. What this is going to do is it's going to iterate through each of the filters, grayscale filter, null filter, embossing filter, whatever the filters happen to be. And for each of these, we're going to call a function called make filter decorator with image. And we pass in the filter, and we pass in the image. And that's going to go ahead and make something called an output filter decorator, which will be a little wrapper around a file. And then we go ahead and we take that output filter decorator, and we tell it to run, which goes ahead and processes this thing to make the filtered output file. So let's go take a look at make filter decorator with image. I think that's residing over here. So you can see you can say make filter decorator with image is just going to make a new object that's a new output filter decorator and the image. And all that does is that just makes a file with that name, and we'll go ahead and when run, it'll apply the image, it'll apply the filter to filter the bytes and store it to a file. So what you can see here from this, hopefully, is that the sequential version of this thing is really simple, and you just write little helper functions, which you then stitch together as part of the actual stream. So if we go over here, let's see if I can go back to this guy. These helper functions are just called at the right point in order to do the processing. That's the sequential version. When we go to the parallel version, it looks absolutely exactly the same. The only difference here is that we use a parallel stream, and we overrode a couple of these methods. So let me take a look at this. So if you take a look here, you can see that we end up using this apply filters method and this apply filters method, which is called in exactly the same way in the stream. This apply filters method, unlike the previous one we looked at, makes this a parallel stream. So if you take a look at this, the apply filters method here and the apply filters method down here, they're identical. It's just that the sequential one uses stream and the parallel version uses a parallel stream. So once again, it's ridiculously easy to be able to take a sequential version that does the streams processing and then make it a parallel stream and just make a few little tweaks, and before you know it, you've got an n-fold speed up where n is the number of cores. So that is just a good example of how streams and functional programming helps to simplify the computation, and it shows how easy it is to transform a sequential version to a parallel version. If you poke around in my directories on the website, you'll find there's other implementations of this application using other Java mechanisms. So there's one that uses completable futures. There's actually a couple that use completable futures. And then there's also some that use things like the Executor service and Executor completion service and all this good stuff. So you can really do a Rosetta Stone comparison between the parallel streams version and more traditional, totally object-oriented Java concurrent versions, and even more advanced versions that use completable futures. And so you can compare and contrast them and see which one runs the fastest and which ones is the easiest to understand and so on. But this is sort of a canonical example of using functional programming. But you'll notice when you look at the implementation carefully, and I won't go through this in too much detail here, the overall design of the program is object-oriented. It uses patterns like template method and factory method and all this good stuff that you're well accustomed to if you're an object-oriented programmer. And it uses that to give you the overall architecture of the design. And then whenever we have to do computation in any great extent, we drop down and we use the functional programming model to structure the computation. And I like that particular arrangement because you use objects for architecture and you use functional programming for computation, and when you combine them together, it's really powerful and very clean. Okay, so let's see. So the last part of this lesson is going to talk about evaluation of parallel streams. We'll talk about the pros and cons and when you would use it, when you might want to use other approaches. So as we saw when we looked at the examples from from search gang, search stream gang, and image stream gang, I didn't run it for you, but if we'd run it, you would have seen that the parallel stream implementations are way faster than the sequential streams implementations, and that's typically in this particular kind of program that's embarrassingly parallel. The speed up is typically a function of the number of cores, so the more cores you throw at the problem, the more things speed up. That's very common for this kind of a program, and as more devices get more cores, right, as you start having quad core and octo core and hexo core, or whatever 16 cores will be, you get increasing speed ups in performance, which is fantastic. You'll also notice if you go back and you look carefully at the implementation of the examples, there's really no explicit synchronization required. We don't have any places where we have any locks. So the reason for that is the way we designed the program, any locking that was needed was handled internally to the Java libraries for things like opening files and reading and writing to files or reading and writing to sockets. All that stuff is handled for us by the Java class libraries. And so we don't have to do any synchronization in our code at all. So all the discussions we've had throughout the course for synchronization may disappear if you use Java 8 streams properly, and you've programmed your code in order to avoid any access to shared data. So if shared state or shared data can be avoided by the way you design things, then you get this wonderful synchronization-free world, which is really cool. Often making changes to go from sequential approaches to parallel approaches are minuscule. We just go from stream to parallel stream. And the Java 8 framework shields developers, us, from lots of low-level details. So we don't have to think about how we split stuff up into pieces. We don't think about how we have to process each piece concurrently. We don't have to think about how we're going to join the results. All we have to do is think about what we want to have done, and the framework does much of the heavy lifting for us, all of which is very cool. I think these examples also demonstrate the synergy between functional object-oriented programming. There are purists out there who believe you should only use objects. There are purists out there who believe you should only use functional programming. I think that's silly. By combining the two together, you get the strengths of each. In particular, you get the computational succinctness or parsimonious behavior with the functional stuff for computation, but you get the nice architecture and object-oriented designs that you get when you focus on hierarchical data abstraction and overriding and all the patterns that go along with object-oriented programming. And Java 8, I believe, does a great job of mixing those two things together. The object-oriented design is easy to understand and reuse. This is the design for the stream gang. I won't go through this all in gory detail, but essentially there's this base class called assert stream gang, and then we have different kinds of implementations for the different concurrency models. So each of the concurrency models localizes where the differences occur, but we're able to reuse the overall framework, thereby making it easier to write a program that tests it all, and it basically isolates change at the edges of the design, which is almost always the win with an object-oriented approach. These hook methods that we have here, like process stream, and then the various streams that go on, help to close the gap between the domain intent and the computations. So the framework is very, very common and reusable and understandable, and then you just sort of fill in the differences in the subclasses, which is good. There are, however, in the interest of full disclosure, there are some limitations with parallel streams. So everything is not, rainbows and unicorns, right? So there are some things to be aware of when you use them. Not every problem can be decomposed cleanly into the MapReduce model. And that's really what a stream is all about. It's about MapReduce. It's about breaking things up into small parts, into subtasks, and then running them each independently. And you can take a look at this article, which will talk about some of the problems with this. And long and the short of it is not everything decomposes this way. And in particular, anytime you have a lot of very subtle dependencies across computations, streams may not work very well because you'll have a hard time getting that embarrassingly parallel flavor that we have talked about if you have lots of computational dependencies in data, typically. If you're careless and you do something like, oh, I'll just replace stream with parallel stream, but the things you're breaking up into pieces, in fact, have dependencies, you'll end up with all kinds of race conditions. And those can be tricky to chase down because you'll think, oh, but I just changed one thing and now my program doesn't work. Well, it's because there was state, and sometimes that state is somewhat hidden from you, and so it's hard to know the problems. And as you hopefully have learned in this class, there's all kinds of subtleties with respect to things besides atomicity. There's also visibility and ordering that will come back to bite you in a multi-core concurrent environment. So you have to be aware of all these issues when you write the code, and sometimes they're hard to reason about. Another thing that's kind of weird is that all parallel streams share the same Forkjoin pool. So you can end up in a situation where if you have lots of parallel streams, they're all using the same pool, which becomes a problem. In particular, it may turn out that one use of parallel streams needs to use a different number of threads than another version. I'll give you a good example. Were we to look at the parallel streams implementation of our canonical Palantir Manager app that we've been using throughout the course to demonstrate all the different concurrency models, one of the things you'd very quickly realize is you can't have a stream that uses the default number of cores, which is, let's say, 2 or 4, because you actually have to have a separate thread for every being that wants to gaze. And if you only have the number of cores, let's say you have 2 cores, but you've got 10 beings, you're going to get deadlocked really fast because only 2 things you're going to be able to look at a time, to gaze at a time. So that's an example where you really would need to then increase the default size of the pool for that parallel stream. But that might cause downsides for some other computation that wanted the parallel stream that only had the number of cores on the machine, right? So because there's only one pool that's shared by everybody, getting that right is hard. The way around that, of course, is twofold. Number one, have a separate program for every use of parallel streams, or every different use of parallel streams. That's one way to do it. And the second thing to do is use the other concurrency mechanism in Java 8 called completable futures. And completable futures give you your own pool for each of the completable futures that you're using. So you can have different pools. We won't have time to talk about completable futures, but they're also very cool. There's also some downsides with parallel streams due to its use under the hood of Forkjoin pool. And you can take a look at this article, which is basically a screed or a polemic going on and on about how evil Forkjoin pool is and what a mistake it was, and how it was a research project that escaped from a university and infected the world of concurrent Java programming. I'm not sure I entirely buy all the arguments. It seems a little harsh, but this guy has spent a lot of time thinking this through, and so it's worth reading it, if for no other reason, just to get a sense of other perspectives on how to write concurrent programs. I think it's really more about knowing when to use the right tool for the right job. In many cases, however, the simplicity of parallel streams, the pro of the simplicity of parallel streams, outweigh the cons in many cases. Not all, but in many cases. And so again, if your goal is just to get things up and running fast, that's often a way to take advantage of parallel streams. The other lesson learned from that is that once you go down the road of functional programming, it becomes much easier to be able to move from sequential to parallel. And that's because functional programming sort of inherently eliminates concurrent modification of state. In fact, if you're a pure functional programmer, the state is immutable. So it makes it really easy to speed it up. It may be hard to understand your program, but it makes it really easy to speed it up through concurrency. And as I mentioned before, I strongly recommend you take a look at this book if you want to learn more about this stuff. It goes into great detail about streams and lambdas and method references and functional interfaces and functional programming and completable futures and so on. And I haven't yet found a more comprehensive coverage of these topics than in this book. I suspect that will change over time as people use Java 8 more and more, but right now that's the place to go.